Great. Now we have Prasant Kumar Sahay, a second semester IISc MTech student in NMCAD Lab. He's working on the application of physics-informed neural networks in aerospace engineering problems.
You can start, Prashant.
Okay. Namaste, respected professors, my dear brothers and sisters. My name is Prasant Kumar Sahay. I am MTech first year aerospace engineering student in Indian Institute of Science, Bangalore. My advisor is Dr. Dinesh Kumar Harusampat sir, and my co-advisor is Dr. Rajnish Malik sir. So today I am going to present application of physics-informed neural network in aerospace engineering problems. So what is pin? Pin is basically a function approximator based on artificial neural network. In pin we try to solve a differential equations. So uh, is pin is applied where only some data and some physics are there, and when there are little data and lots of physics, we cannot apply pin there. And if only data no physics are there, then we can also not apply pin in that scenario. Okay, so pin can seamlessly integrate data and governing physical law, and pin exploits the input data and automatic techniques of automatic differentiation in order to create approximation of all terms involved in the differential equation and the initial boundary condition of investigated model at every point in space and possibly in time. So this is the basic introduction for pin. Now we are going to take some examples. So this is the example of second order differential equations where we try to solve this differential equation using pins. So uh, here there are two blocks which you can see in the pins representations. So first block represents the basic back propagations, and the second block in which blue color small blocks are there is basic pins. So in back propagation techniques, we first train the network, and then we apply the physics in the second block, which is represented in the blue. So so by using this technique, we can solve this differential equation, and it will give an approximate solution, which is represented by u of x, u hat of x, which is equal to neural network of x. So this is the solution for the differential equations. And now we take some practical examples. So this is the practical examples which I am going to take. This is the 1D damped harmonic oscillator, and the governing equations are there as you can see there. So in the first plot, which is on the left side, you can see that there is a plot of 1D damped harmonic oscillator, and when we apply physics informed neural network to solve this differential equation, uh, and after training so many steps, we can see that the neural network prediction and exact solution are coinciding each other. So here you can see that in the right side of GI images, uh, image, the neural network prediction and exact solution are coinciding each other. So we can see that pin is effective in solving differential equations. Now the second example we take is the Navier-Stokes equation. We know that Navier-Stokes equation cannot be solved analytically. So by using pin, we can approximate the solution of Navier-Stokes equation. So in this Navier-Stokes equation, the first equation in the box is the first equation is the continuity equations, and the below three equations are the momentum equations in x, y, and z direction. So we can see that we are giving x, y, z, and t as an input, and we are getting u, v, w, and p as an output. So this is the basic structure architecture of physics informed neural network for solving Navier-Stokes equation. And here our goal is to try to reduce the loss. So which is the main objective of our physics informed neural network. Because when the loss is more, the model will be not effective. and when the loss is less, then the model will be effective. So this is the example of Navier-Stokes equations. Now we take the example of a structural engineering problem in pin using pins. So this is the rod with distributed force, as you can see here. This is the rod with distributed force, and mm, there is a cross-sectional area A, which is represented by A, and the Young modulus of elasticity is represented by E. So you can see the governing differential equation for the rod with boundary conditions. So we can solve this differential equation uh, by using pins. And when we solve this differential equation, there are certain steps we should try to consider. The first step is to we have to input the data for neural network and the collocation points for the differential equation, which is there. As you can see that the collocation points are u of 0 is equal to 0 and du by dx at x is equal to L is equal to 0. So these are the boundary conditions which we have to take, and weight, bias, and number of epochs and the physical parameters of the mechanical problems should also be considered. And the second step we should take is that we should uh, activate some weight and bias, which is in the feed forwarding network. So in the next step, we can see that. So this is the basic illustration of two network problems. A basic illustration of two network problems. So, so in the first, as I have already mentioned, this is the feed forwarding network left side, and the blue, which is on the right side, is the physics informed neural network, uh, physics informed machine learning part. So in this part, in the physics informed learning part, we have to construct a loss function. As you can see that there is a loss written. So we have to construct the loss function and then calculate the derivative of loss function concerning all trainable parameters, starting from the last layer, which is the which we also called back propagations. And then we have to minimize the loss function using an optimization techniques. And then we have to update weight and bias parameters in the neural network, and then we have to repeat all the steps. This is our training set. So we have to repeat all these steps, and the more we repeat the step, the more accurate our solution will be. So here you can see that after repeating so many steps, there is a graph, there is a plot of approximate solution which is given by pin, and exact solution which we can calculate analytically. So the graph will be the analytical solution plot, and the pin plot is approximately coinciding. So here we can see that pin can also effective in solving structural engineering problems. So so by using pin, we can also solve many aerospace engineering structural problem. So this is the example of a structural engineering problem. And now we can say that if by using pin, it will be beneficial for Airbus digital twin effort, because it is also a very good technology innovations. And the second point is this technique can be easily applied to the complex and mechanical problems that cannot be analytically solved. Uh, as we have already seen that Navier-Stokes equation can also be solved by using pins. So it is effective method, and it can also be applied in dynamic problems, direct and inverse problems, contact problem in continuum mechanics. So we can also use this uh, pins in inverse problem, which is very hard to solve. So, and pin research has gone support from researchers and technology practitioners in recent years. So it is very good method, and we should apply this method in solving many aerostructures problems. Uh, these are the references which I have used for making this PPT. Thank you. Thank you.
So the method you start to develop and you will develop if I understood more in the next month. I don't know. So, but what is the first application you would like to do? You mentioned a few in the conclusion. Which you think that you can be start with?
I have studied in composite class. There are some differential equations. So I will try to solve those differential equations by using pins.
What else?
Pardon?
Specific? Can you be specific on which you want to apply?
I Presently I do not know remember that differential equation, but I will I will try to solve that equation. And for solving this equation, I have to uh, I have to do programming in Python by using TensorFlow. So I will solve this. These are the second order partial differential equations.
Prashant, can you please tell me that what was the data set that you used for your NDS solution?
Data set. Uh, Actually, I have not uh, researched on that Navier-Stokes equation physics informed neural network. Uh, it is another domain, and my domain is on a structure. So I have just presented that it is effective in solving equations, a differential equation which cannot be analytically solved.
Yeah, of course. I mean, it is $1 million equation.
Yeah.
But I just want to know that after you got a solution, did you verify the answer by some manner?
No, we can verify it experimentally. Or there are another method, finite element method, finite volume method. We can also check by using that method also.
Finite element method for negative.
Pardon?
Just clarify, like how Renuka introduced, he's just 2 weeks into the master's program. So he's just looking at it from a conceptual point of view. He's still identifying the problem, what he would like to apply to, but he's essentially interested in physics, based neural networks. So he's just looking at pins as an option, but he wants to identify an appropriate problem in aerospace engineering to apply it to. So most of what he was showing were based on the literature from his understanding of how pins is used, where it is used. Understood. Thank you.
Thank you, Prashant.
Thank you. Thank you.
Sir, you can ask the question, sir.
Okay. Prashant, I am just curious to know, like when you go to, let's say, slide number 5, you are shown on the, you have some XYZ on the left hand side and UVW on the right hand side. What is your input and what is your output? And what is this? If I understood, blue dots represent hidden layers. Now, in what sense the activation function will be happening, and how the inputs will be connected with one node to another kind of one, and where this physics is getting involved. If you look at any kind of artificial neural network framework, it's very similar to that kind of one. Now, where exactly the physics based artificial neural networks is getting into picture?
Sir, here X, Y, Z, and T, U is a input, and U, V, W, and P are the output. So U is the velocity in the X direction, V is the velocity in the Y direction, and W is the velocity in the Z direction, and P is the pressure, and T is the time. And there are some weights and bias, which I have to do some research on that. And by using that weights and bias and the neural network, we are getting the output as U, V, W, and P. And the physics involved here is the differential equation, which I have mentioned there. Uh, the first one is continuity equation, and the other three are momentum equation in X, Y, and Z direction.
I mean, we may not look at Navier-Stokes equations in the beginning. Maybe in the slide number 6, you're just taken very simple problem, either bar or a beam kind of a problem. So even if you look at this kind of a problem, let's say, what is the role of this boundary condition? Can you just illustrate? If you're looking at a mathematical equation, AE into D square U by dx square is equal to minus CX. This is fine. Now, how do we translate a mathematical equation of this nature for a given input and for a output? Let's say your U is as a displacement as an output. How do you connect this, and how do you able to bring the physics into the problem?
Sir, we have to use boundary condition as I have already mentioned. We need some data and some physics. So physics is in the model of differential equation. So here physics is the differential equations, and data is some data which is there is the boundary conditions. So we can use boundary condition as some data, and while doing this neural network, we have to do some uh, back propagation and feed forwarding. So in back propagation, there is a loss function. So our goal is to minimize the loss. So by using this, we can solve this differential equation.
I'm sorry to say, but I am not fully convinced with the kind of explanation. Maybe you can, explore more.
Yes,
Because
sir.
if you look at in any traditional ANN or a CNN kind of one, what we have is an activation function. Let's say if you are looking at a blue kind of a structure over here, U is the predicted value. And you are trying to figure out a prediction minus your actual value, which can be given as a loss. Now you are minimizing this loss function. Let's say even if you do any finite element analysis or any other semi-analytical method, we are trying to minimize the loss function. So that is where you are trying to push it back from the what is the output loss, or what is the difference. Loss is a term which computer science people might be using, whereas in our case, maybe it is the difference between actual value and the predicted value. Now that prediction, how much is closer to your actual value, and how do you propagate this back, whether it is in the first order differential equation, second order differential equation, and trying to figure out to the the variable. So I think, please try to look at and give a proper illustration so that we can have much more visibility of this particular very useful method of physics-based ANN.
Yes, sir. Sir, actually, I'm new in this field. I have just 1 month of experience, and my coursework is also there. So that's why it is not
sorry,
very
I didn't know that. Okay,
no problem, sir. No problem, sir. No problem. Thank you, sir.
Ramesh, we thought you were ragging in spite of knowing.
I'm sorry, I didn't know that. I just joined.
No problem, sir. No problem. Thank you, sir. Okay. No problem. Sir.
So tomorrow his boss will be there. Rajneesh, you can ask him.
We can interact. All right.
No, thank you, but actually it really helps these kinds of questions, even though they're new, it tends to put them on the right line of thinking, because these are questions they are supposed to ask themselves. So when you're presenting something, you should know what is behind it and things like that. So I think it's very important to understand what is the logic, what is the physics behind. So these are tools and techniques. So those are much easier to learn, but it's the actual problem that you're going to be implementing on. You should know what are the limitations of your tool, whether it's applicable there or not. So many of the questions which Harsh asked here, as well as what Professor Ramesh asked just now, I think these are all things that you should ponder upon and find answers for as quickly as possible. That will set you on your target much faster and more efficiently. Okay.
Yes,
So recording, even if you don't remember these questions, I think the recordings will be available, so you can take a look at that. Once again, note down the questions and try to think on those lines. Yeah.
yes, sir. Yes. Thank you, sir. Thank you, sir.
Good, but good job. I really appreciate it. In such a short duration, you have come up with a reasonably good presentation. Thank you.
Thank you very much, sir. Thank you. Thank you, sir.